today I'm going to explain integration. Now, before I get to the informational section of this, I feel I should mention that the informative clips I'm going to be using are actually from an integration video I made about 5 weeks ago. Now, the issue with this, and the reason I didn't show you guys it, is because I explained a lot of stuff, and it ended up being around 30 minutes in length. Now, I felt that was too long to upload, especially for an informational video, so I decided to cancel that, and I explained some of the things I explained in the video in separate videos. Actually, I split off a couple of videos from it, which were my limits video and my summation video, which I recommend you watch both of those before you continue to watch this one, because, I mean, it's kind of important that you know that stuff to understand what I'm going to talk about in integration. But nonetheless, the reason I tell you this is because the clips may sound a little weird, as though I'm referencing stuff that isn't there, because I am actually referencing stuff that I'm not showing you. Now, the references aren't too distracting, and the information is all good, so I decided to keep the clips instead of having to reshoot all new ones. But I just wanted to let you guys know this, just in case it sounded a little weird to you. Alright, so today I'm going to explain integration. And what integration is it's the method to figure out the area under a curve. So let's pick a section on this curve, just randomly. And it obviously doesn't matter what section you pick. But we'll go with this. Now, it obviously isn't easy to figure out the area under a curve like this. I mean, if it was, I wouldn't probably be explaining it. It's not easy like figuring out the area of a rectangle, where it's just, you know, the width times the height. Now, of course, with that being said, we're actually going to use rectangles to figure out the area under a curve. We're essentially going to divide this into a bunch of rectangles. Now, let's say we just go with one rectangle for now. We've got that, so we've extended it, so we now have a rectangle. And we multiply the base times the height, we get this whole area, which, as you can see, it has this whole extra section here, and is actually quite a bit more than the actual area, you know, under the curve. Well, let's say we just divide up this rectangle now into two rectangles. So we've got two rectangles instead of just one. So we've got it like this. Well, as you can see, that by just using two, we've already cut out this whole section here. So the area of these two rectangles is closer to the actual area under the curve. And as we get more and more rectangles, the areas of those combined rectangles gets closer and closer to the area under the curve. So our goal is to get essentially get an infinity number of rectangles. Now, the issue with this is, you'll notice that by having two rectangles, we essentially cut the width in half. Because you see, we have this one rectangle, which was a full width. Now we have two rectangles, each of essentially half width. Now, by having an infinity number of rectangles, they're going to be infinitesimally small width. And since we can't multiply an infinitesimally small anything by an actual number, such as, you know, the height, we have to, you know, do some working with it. And to get into the actual integration, I need to explain a couple things first. Now, the last thing I need to explain is how to find the width and height of a rectangle. And what we're doing is, first we need to figure out the width of the section of the area that we're figuring out. So, we're wanting to figure out this section of the area, we need to figure out this width. Well, we can mark the first point, or the starting point, by A, and the last point by B. And the width of this section can be modeled as B minus A. And I can show you how that works, because B is this full distance, A is only this distance, and we want to figure out this distance. So we can take the B and then get rid of this A segment. Like, for example, say we have it going from 3 to 1, so the width would be 3 minus 1, or 2. That makes sense. Now, if you remember from the beginning of the video, when we had one rectangle, its width was this full b minus a. You remember? One rectangle, full width was b minus a. Well, when we had two rectangles, each of their width was half, or b minus a over 2. So we can model the width of each of the rectangles by the width of the section divided by the number of rectangles, or n. And say, for example, we're going to split this up into 4 rectangles. I know it's getting a little messy here, but just bear with me. So we're dividing this up into 4 rectangles. And since the width of the total section is 2, we do 2 over 4, and we get 1/2. Which means that each of these are 1/2, and 1/2 plus 1/2 plus 1/2 plus 1/2 is 2. So, I mean, that's how you can figure out the width of each of the rectangles. It is modeled by b minus a over n, where b is the end of the section of the area of the curve you're finding, a is the beginning of that section, and n is the number of rectangles you have. Now, finally, I'm going to explain how to figure out the height of a rectangle. Now, you want the height of a rectangle to go up to the curve. So, at any given x-coordinate, you want it to go up to the curve. So you want to figure out, from the x-coordinate, you want to figure out how it goes, the height to the curve, or, the y-coordinate. So you need to figure out a way to relate the x and the y-coordinate. Luckily, since this is a curve, we have an equation for the curve that relates such x and y coordinates. So we have a function, x, and if we plug in any x-coordinate into the function, that will give us our y-coordinate, or our height to the curve. Now, we just need to figure out how to model x. And we can actually do that by taking our width, or b minus a over n. So we have our width of one of our rectangles times the number of rectangle we're looking at, or I. So we're looking at the ith rectangle. So, say we want to look at so we go over ith rectangle width. So we want to look at the third rectangle, so we go over 1 rectangle width, 2 rectangle widths, 3 rectangle widths, and then then we can just plug that in for x, and that will give us the height to the curve. Except, say we go back to our original example, and we have 3 here, and 1 here, and 4 rectangles, each of width 1/2. Well, if we go over to the ith rectangle, which would be I times, or 3, or if we go over to the third rectangle, we'll say, which is 3 times 1/2, we go over 3/2. Well, 3/2 is right there. So what we need to do is we need to add a to that, to indicate where we start. So we need to have a to indicate, alright, so we start here, and then we go over our ith rectangle widths, and that will give us our x-coordinate. So the height of a rectangle can be modeled as the function of the starting point so we have the starting point, and then the width of a rectangle times whatever ith number of rectangles we want to go over. So the height of a rectangle at any given rectangle can be modeled as that. Now, finally, we can figure out the area under a curve. And keep in mind, we're splitting it up into rectangles. So, we multiply the height, which we modeled earlier, which was the starting point times the width of a rectangle, times however many rectangles over we're going. So that's the height, then, times the width of a rectangle. And this gives us the area of one specific rectangle. Now, we want to figure out the area of all of the rectangles. So we add the sum. So we figure out the sum of the first to last rectangle. And you notice that there's the last rectangle is n, and the number of rectangles we have is n. Well, keep in mind, say we have 10 people in the room, a first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th person. Well, the 10th person is the last person, and it is also the same as the number of people in the room. So that's just kind of how it exists. The last thing of a series is also the same as the number of things in the series. That relation exists. Now, we want to figure out that as we essentially have an infinity number of rectangles, and the rectangles get infinitesimally small, that will give us the actual area under the curve. So what we do is we need to figure out this as the limit of n approaches infinity. And this is our equation to find the area under a curve. Now, I'm going to give an example of how to find the area. And the example I'm going to use is for the function f of x. The function is going to be x squared, which is, this line right there. And we'll find the area from 1 to 3. So a equals 1 and b equals 3. So we're going to use this as our example, so we're going to find the area of this using this equation. Now, we can simplify some of this stuff off right now. We can get rid of the b's and a's in here. So we can simplify the width, so we have 3, which is b, minus 1, which is a, over n, so that simplifies to 2 over n. So that's the width. And then the height, we can simplify down to have 1, which is a, plus then the width, which I already wrote down over there, but just for the sake of completeness, I'm going to do it here as well. So we have our new width and height that we're figuring out, or that we're going to now work with. Now we can start working with this equation. And what we have is we have the function of 1 plus 2i over n, which just means that we plug in 1 plus 2i over n for x. So let's go ahead and do that. So we have 1 plus 2i over n squared, which is the same as 1 plus 2i over n times 1 plus 2i over n. Or 1 plus 4i over n plus 4i squared over n squared. Now, I'm not going to go through the work on that. You can just trust me on it. If you don't believe me, you can go through it yourself. Just remember the FOIL. Now, we then multiply that by 2n. 2 over n, I should say. Because this is our height, and then we multiply that by our width. And that will give us 2 over n plus 8i over n squared plus 8i squared over n cubed. And we want to find the sum of all of those rectangles, as the limit of those rectangles approaches infinity. We are now at this point, and if you remember from earlier, we can split up the sum into a bunch of individual sums. So we have our first sum, which is 2 over n, plus our second sum, which is 8i over n, plus our third, or 8i over n squared, plus our third sum, which is 8i squared over n cubed. And we can just split up the sums into those three terms, like that. Now, what we can also do is we can bring the coefficients out front, which I also mentioned earlier. And keep in mind, n is technically not a variable, but a number. I mean, we're having it be a variable, but essentially, we want to plug in infinity for n. So, in our case, n counts as a constant and not a variable. The only variable we really have is I. So, since n is a constant, we can bring the n out front. So we have 2 over n times this first sum, which just simplifies down to 1. And then we have 8 over n squared times our second sum, which is then just I. And then we have 8 over n cubed times our third sum, which is then I squared. So we have split up the sums into their own separate sums and have brought the coefficients out front. So, now that we're at this point, our summation equations come in handy. So, we have the limit as n approaches infinity, because we need to keep that in front of it at all times. And then we have the coefficient, and then we have this. And since 1 is a constant, the summation formula, remember, was n times the constant. And since n times 1, so that just gives us n. So we have that. And then we have our next term, which is 8 over n squared. And the summation formula for I was n times n plus 1 over 2. And then we have 8 over n cubed. And our summation formula for I squared was n times n plus 1 times 2n plus 1, all over 6. So we are now at this point. Next, we can do a little bit of simplifying. And these two n's cancel, leaving us with just 2, plus then one of these n's, and that n cancel, and this 2, and then that this 2, and then this 8, so that simplifies us to under 4. So we're now left with 4 times n plus 1 over n. And then here, one of these n's cancel, leaving us n squared, and that n cancels. This 6 simplifies to a 3, and this 8 simplifies to a 4, because the 2's cancel. So we now have 4 times n plus 1 times 2n plus 1, all over 3n squared. Next, we need to get the top things so they're not things multiplied with each other, but just one polynomial. So essentially we need to do some foiling. So, we have the limit as n approaches infinity, as always. And then we have 2. That doesn't need any simplifying. That's as simplified as can get. And then we have 4n plus 4 over n. And then here we have, 4 times, that's 2n squared. And then that's 1n, so we have plus 3n plus 1. And that is all over 3n squared. Now, at this point, I'm going to go ahead and just distribute this 4 off to the side. That would give us 8n squared plus 12n plus 4. So we can just plug this in at the top now. So we are now at this point, which we have the limit as n approaches infinity of 2 plus 4n plus 4 over n plus 8n squared plus 12n plus 4 over n squared. So we are now at this point. And now we can finally get rid of this n to the as n approaches infinity thing. Well, we're going to now have n approach infinity. Well, as n approaches infinity for 2, that would, simply just be 2. And as n approaches infinity for this section, remember earlier when I talked about limits as the number approaches infinity, for a polynomial like this, we only look at the highest power. Now the highest power for these are both n, and since there is a highest power of n on the top and a highest power of n on the bottom, we look at their coefficients. The coefficient for that is 4, the coefficient for that is 1, so as n approaches infinity, this section simplifies down to 4, which we then add to the 2. Same kind of thing for that one. We only look at the highest power, because we can ignore the rest of that stuff. I explained it earlier. So this will simplify down. This is actually supposed to be a 3 in front of it. My bad. So that simplifies down to 8/3. So as n approaches infinity, we then are left with this, which we can just add together. 2 plus 4 is 6, which we can then add to the 8/3 by multiplying 6 times 3, which we get 18 over 3. So we then have it as 26 over 3. So that is the area under the curve of x squared from the x-coordinates 1 to 3. So that is how you would go about figuring out the area under a curve. But yeah, I hope you enjoyed it, hope you learned something, and see ya!